All right, I guess we better go ahead and get started. Hello, everyone. Today is June 21st. It's 5:30 p.m. and I'm getting ready to jump into chapter 14. We may also get into chapter 15 a little bit. But if you look at chapter 14, you'll see it is called uh, Oscillations. And the first section, of course, is oscillations of a spring, and that brings us back to the idea of Hooke's law. So I just want to start off by giving you a little bit of background information on the equations associated with that. So I'm going to go ahead and share my screen with you guys so that you can see it. Of course, we don't have anybody here right now, so I might not pause to ask if anybody has any questions. But if more people come, I'll remember to do that anyways. Of course, the beauty of a video is that you can pretty much pause anytime you want. So make sure you do that if you need when you're actually watching the video, and that should help. All right, so we're looking at, as I said, the sections 14.1, oscillations of a spring, and what we learned was Hooke's law told us that if you apply a force F to an object, and this could be like a rigid object like a 2 by 4, or it could be a string, and that force could be a tension, or it could be a 2 by 4, and that force could be a compression or a tension. And if you apply a force to that object to try to compress it or to try to stretch it, then what we find out is the stretching or the compression, the changing of the length of it, x, will be given by negative k times x. And what we mean by the F is, in this case, the F is the actual force that the object will apply back to you. So if you're applying a force of, let's say, 100 newtons in the positive x direction, then that's going to tend to cause the let's say it's a 2 by 4 and it's set at x equals 0 and x equals 3 meters or something like that. If you had that and you had the 3 meter mark held down and you compress it by pushing in the positive x direction, then you're actually compressing it, and what's going to happen is that compression is going to cause it to shrink from 3 meters long to a little bit less than 3 meters. The amount less we'll call x, and what Hook is trying to tell us is that if you find out specifically what x is, and you know what the force is, then you can use F equals k times x to figure out what the k is, and that'll be a property of that particular object. And more specifically, if it turns out to be for like a 2 by 4 made out of spruce or pine or fir, then you'd expect it to be roughly the same thing for all similar 2 by 4s. Specifically, especially if you have them all spruce or all pine or all fir or something like that. The negative is actually telling you that it's a restorative force. So the force that the actual object applies to you, like if you're pushing it in the positive x direction, then that's going to cause a compression in the positive x direction, and that multiplied by negative kx means the force that the 2 by 4 is going to apply to you is in the negative x direction. So that's what the negative is, and it's all about a restorative force. So that's the force exerted by, in our case, we're going to use it as a spring, but it's actually true for 2 by 4s and lengths of steel and stuff like that. But we use it specifically as a spring because it turns out that if you try to compress a 2 by 4 or an iron rod or something like that, you have to use such large forces that it becomes potentially dangerous. But if we apply it to a spring, it works better and actually works over a lot larger range. So we often call K the spring constant, but in actuality, it's just some kind of constant associated with the object. In addition to that, we could say that the external force is given by F equals, they'd say like this, F external is equal to K times X. And that's the real uh, force that you're applying. So when you apply a force in one direction, it causes a spring to compress, or a spring or a 2 by 4 to compress in that same direction. But the 2 by 4 or the spring is going to apply a force to you, F, in the left equation, given by negative K times X. So that's all about. Uh, in addition to that, we're going to say, like I said, it's mostly restricted to springs, but in reality, it applies to everything. It's just like I said, the X would be very, 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 very small unless you use really large forces. And when you start to use really large forces, it gets really dangerous. With that in mind, we got to remember that springs actually oscillate. You've had enough of experience now with labs that you know about oscillations and frequency. So I'll just remind you that the frequency is the number of cycles per second. And because of that, we get the frequency is 1 over the period, or the period is 1 over the frequency, and t equals the period of oscillation. So, frequency is the number of cycles that occur every second, and of course, that means the frequency usually has units of CPS in old literature, but in modern literature we call it the hertz. And the period, of course, will have units of seconds generally, or it could use years or months or days or whatever. It doesn't really matter, but normally the fundamental unit would be the second, and the fundamental unit for frequency would be the hertz. So those are a couple of equations we need to do. Now, in addition to that, I'm going to tell you that if we actually apply a mass on a spring, so let's imagine for a second that we have a fairly frictionless surface on which a spring is mounted, and you have some kind of mass on it, for instance, then the spring would come out like this, and the mass would be right here, say, and it's fairly frictionless, so this would be the mass m. The spring would have a spring constant k, and if you, for instance, give it a pull, so let's apply a force this way, then what will happen is the spring will actually stretch by a certain amount such that the mass ends up over here, and what we're saying is this quantity right here is the x we're referring to. So that's what happens when you actually apply a force to a mass to move it along a spring. Now, we can use Newton's second law to explain this, and remember Newton's second law is the summation of the forces is equal to mass times acceleration, and that's technically a vector equation, but in this case, we're actually imagining it being all in one dimension, so we don't have to do that. And I will say this was frictionless. But, and I'm trying to remind you this will be frictionless because I'm setting up this equation for it. Now, what that tells us is m a, and remember a is d2x over dt squared if we assume it's in one dimension. If it was in three dimensions, we might call that d2r over dt squared, where r is the position vector. But in this case, we're just going to say d2x over dt squared. There's the ma part, and that's equal to, according to Hooke's law, negative k times x. Now, this is kind of cumbersome writing it in this Leibniz type notation, this dx over dt. So what we often do in the physics world is when we're taking a derivative with respect to time, we call it a dot. So in this case, this would be x double dot and an m. And not only that, I'm going to go ahead and take the time and add kx to both sides. So I'll get mx double dot plus k x is equal to 0, and this is called the simple harmonic oscillator equation, and it causes what we call simple harmonic motion, or SHM. So this would be the simple harmonic oscillator, and it causes SHM. We normally don't write it this way though, so what we often do is we go ahead and multiply both sides of the equation by 1 over m, and whatever you do to one side you must do to the other, and as long as you do, it's okay. The only damage, of course, is if you multiply through by 0 or divide by 0. Those are problems. But either way, once we've done this, what we get is x double dot plus k over mx is equal to 0, and this is what I want you to recognize as the simple harmonic oscillator equation. So this is the simple harmonic oscillator equation. Now, if you once you've covered this, you'll know that this equation, of course, applies to a lot of things, and that's why we study springs so much in physics. It's not that the world is just packed full of springs; it's just a lot of equations have the same form, but the main form is a second order derivative in time plus some constant, in this case it's k over m, times the zeroth order derivative, and then all that's equal to zero. So that's the simple harmonic oscillator equation, and any solution to this exemplifies what we call simple harmonic motion, which is also called sinusoidal motion, as you'll see a little bit later. Now, if you were taking differential equations, they would tell you, hey, isn't this really neat? If we could only find a function that when you take its derivative, you get the same function back, but maybe a constant in front of it or something weird like that, then that would be super, super nice, right? And that's the way they'll proceed. And that way is perfectly fine. It does work, and it can come back to give you the exact solutions that we're going to give you. What you'd normally use is you'd say let x equal a times e to the row t. So you could do that. That's what you do in a differential equations class in diff EQ. We would let x of t equal to some constant times e to the rho t. And the reason why is because the derivative of e to the rho is rho times e, or excuse me, the derivative of e to the rho t is rho times e to the rho t. So you literally get the same function back, but with a constant in front of it. And that's exactly the sort of bill we would like for this x function. But it turns out that sort of the sine function or in sort of the cosine function does that. In reality, it's not really exactly that way because, if you take the derivative of sine, you get cosine. And then if you take the derivative of cosine, you get negative sine. So after two derivatives, you get back to where you are to the same function again with just a constant in front of it. But the first derivative is not that. That being said, we're going to do something else. In physics, and this physics course slash book slash text, we let x equal to a cosine omega t plus phi. It turns out, just like we've learned the fundamental theorem of algebra, which basically says that if you have a second order polynomial, then you expect two solutions. If you have a third order polynomial, you expect three solutions. If you have a fourth order polynomial, you expect to have four solutions, so on and so forth. And in order to do that, you obviously have to have, in the case of a second order polynomial, you'd have to have two sort of initial conditions, if you will. And if you had a third order, you'd have to have three conditions or something along those lines to actually figure out what the constants are. Because a third order polynomial would be a x cubed plus bx squared plus c x plus d. So that's actually four constants. And obviously, in order to determine those four constants, you need a total of four equations, and that sort of goes with it. But in the case of differential equations, it turns out that whenever you have a first order derivative in a differential equation, you have to have one initial condition. If you have a second order differential equation, you have to have two initial conditions. And what that does is, if you could imagine, what undoes a derivative is an integral. And if you ever integrate something without actual limits of integration, you have to add a constant. So you can imagine, hey, if I got a second order differential equation, I've got to integrate it twice, once to get rid of one of the derivatives, the second time to get the other derivative. So that would make you think that you're going to have two integration constants. And in order to have two integration constants, that means you have to have two arbitrary values, which in this case I'm saying is going to be a and phi, but it might even be omega, but we're going to see in a second that it's not. And that's why I actually said x is equal to a cosine omega t plus phi, because I know the omega is going to be a characteristic of the actual simple harmonic oscillator equation, but the a and phi is what's going to be filled in by what we call the initial conditions. That's just something that goes along with solving differential equations. It's just like when you have to integrate a function without about limits of integration, you've got to add an integration constant. And in this case, it's a second order differential equation, so you have to add two integration constants, and I'm calling them a and phi. So hopefully that makes some sense to you. Now that we have that, I'll show you how we go about doing this. I'm going back to green. So we're going to say x dot, which is, as I said, dx over dt, which equals d by dt of a cosine omega t plus phi. Now, the a is just a constant, so that's just going to come out in front. And then we're going to take the derivative of cosine. And of course, the derivative of cosine is negative sine. And then when you take the derivative of cosine, you're actually taking it with respect to the argument, which in this case is omega t over phi. So then you got to take the derivative of omega t plus phi with respect to t, according to the chain rule. So when I take the derivative of cosine omega t plus phi, I get negative, and I'm going to leave a space here on purpose, sine omega t plus phi. And now I got to take the derivative of omega t plus phi with respect to omega, and the derivative of omega t plus phi with respect to omega is just omega, or excuse me, with respect to t is just omega. Hopefully I said that correctly most of the times. So again, I took the derivative of cosine omega t plus phi with respect to time. That gave me negative sine, and then I got to take the derivative with respect to time of omega t plus phi, and that gave me omega. So my result after taking the first derivative is x dot is equal to negative a omega sine omega t. Now x double dot, which is a second order derivative, okay, that's also equal to d by dt of this new function, which is negative a omega sine omega t plus phi. And now we can see that I'm going to, again, have a constant out in front. This time I'm going to make the negative right here. I'm going to make the a right here. I'm going to make the omega right there. Those are all the constants I just pulled in front. Now I'm going to take the derivative of sine omega t plus phi with respect to t. And of course, the derivative of sine is cosine. So I'm going to write cosine, and I just write down the argument that cosine had, which is omega t plus phi. But now I've got to take the derivative of omega t plus phi with respect to time, which gives me another omega. So this becomes negative omega squared, negative a omega squared cosine omega t plus phi. So now I have the second order derivative, and I can plug it back into the simple harmonic oscillator equation. So simple harmonic oscillator equation implies we now have negative a omega squared cosine omega t plus phi plus k over m. And then now we're going to put in the original function for x, which we said was a cosine omega t plus phi, like that. And that's all equal to 0. So just in case you didn't understand what I just did there, this is x of t that we hypothesized, a cosine omega t plus phi, and this part right here is x double dot of t. So basically this is just the simple harmonic oscillator equation, except now I've plugged in the actual values of the functions. So now that I have that, I can see I have a common factor of a cosine omega t. And to be honest with you, this has to be true because it's Newton's second law of motion. This has to be true at all times. So let me factor out all the stuff that we have in common here. And when I do that, what I get is negative omega squared plus k over m times a cosine omega t plus phi. All that is equal to 0. Now, again, this has to be true for all time, so I can't make this 0 by forcing the value of cosine omega t to be something. So in fact, I have to force this other part to be equal to 0. So this part must equal 0. And because of that, we get we get omega, and it could be plus or minus, but we take by convention, we're just going to say it's the positive square root of k over m. So that's what actually omega is. And as I told you, the omega is not one of the variables that come from the initial conditions of the simple harmonic oscillator problem that you're solving. Omega is a characteristic of the initial values, specifically what is the k, the spring constant, and what is the m, the mass on the spring. So we now know that, and we can tell, for instance, that the solution really is if the equation is x equals, so I'll write it this way. If x double dot plus k over m times x equals 0, then x of t should be given by a cosine square root of k over m times t plus phi, and the initial conditions will be used to determine a and phi. And we'll do that a little bit later, but that's the key. So that's the whole solution to the simple harmonic oscillator. And it gives us what we call simple harmonic motion. And I should go ahead and point out that as we learned before in rotational motion, and as we learned before when we were just doing mass on the spring, that sort of thing, we did learn that omega is equal to 2 pi times f, which I could have written that a little bit worse, but not a lot. So omega is equal to 2 pi f, which is also equal to 2 pi over the period. And then, of course, we also know that the frequency is 1 over the period as well, which is what we use there. So that's some background information. The amplitude can be found again from initial conditions. For instance, your book talks about if we imagine pulling the spring out, or the mass on the spring out to some initial position. In other words, we stretch it out like I showed in the little picture above to some initial value x, and then I let it go. If it's frictionless, what's going to happen is the spring is going to pull it towards it, and the spring's going to do it whether it's frictionless or not, but it won't degrade. In other words, it'll always come back to that same amplitude every time. But whatever that distance that I pulled it out was, that's going to be the maximum amplitude. Even if there is friction, that's the maximum amplitude. But if there's no friction, it'll be the amplitude that repeats itself over and over. But when I did pull it out, the force that the spring applies is pulling it back the other way. So the spring's going to pull it back. It's going to speed up, speed up, speed up, speed up until it reaches the equilibrium spot for the spring, which was the original green drawing. At that point, the velocity's reached its maximum value because it was speeding up all the time until that instant. And then as soon as it goes past the equilibrium, then the spring is going to start pushing it back against it the opposite way because it's now going in the negative x direction. And F equals negative kx would suggest that the F is now going to be in the positive direction. So it's going to slow down, slow down, slow down, slow down, slow down. And then it'll come to a stop at x equals negative a, if you called the equilibrium x equals 0, and of course, the initial stretch would be x equals a. So now we've pushed it back to negative a. It comes to a stop, and then it starts to speed up in the positive x direction, speed up, speed up, speed up, speed up, until it reaches equilibrium, at which point it reaches its maximum speed, and then starts to slow down again. So if we were to actually do that, then our initial conditions would be that at x equals 0, that means that or excuse me, not at x equals 0, at t equals 0, x is equal to a. So that's one initial condition. X equals a at t equals 0 is a initial condition. And then you could plug that in, and using this equation, the specifically x is equal to a times the cosine the square root of k over m times t plus phi, and you plug in t equals 0, and you get a is equal to a cosine of phi. Now, that could give us some idea what phi should be. And in fact, with this condition, you actually know that phi should in fact be 0. It could also be 2 pi. It could also be It could also be negative 2 pi, so on and so forth. But that's a initial condition, but it only allowed us to determine one, specifically the phi, and the a is already in there, and that just happened to be the quantity we had. So you'd see that that's why we called it a to begin with. Now, you'd also like to know what is the velocity at t equals 0. That's the other initial condition. And normally it's the velocity at t equals 0 and its position at t equals 0. Those are your initial conditions. And the velocity, of course, is the x dot. So remember, I'll write it right here. This is equal to the velocity as a function of time. And not only that, when you took the second order derivative, that is the acceleration as a function of time. So just keep that in mind. But now, if you had the initial condition at t equals 0, x is equal to a, then you would say, okay, a is equal to this variable a. Maybe you should use a different variable other than a for the initial condition, but or for the a and the function, either one. But one of those two should be different, and you'd have a cosine phi is equal to this amplitude. Okay, but you don't really necessarily know because that's two unknowns. You've got an a that was built into the equation for in front of the cosine, that's an unknown, and you've got a phi that's an unknown. You've only used one equation. There's no way you can get those both. So now you need to go about applying it to the initial condition for the velocity. And if you said the velocity was equal to 0 at t equals 0, then that would say we were going to set negative a omega sine of phi equal to 0. And that, between those two equations, we should be able to determine both phi and a. And as of course, what you'll figure out is a is the amplitude. But you can also do another scenario. You could say at t equals 0, x is 0, but at t equals 0, v is positive v, or positive v0 or something like that. Now you have two initial conditions. You could solve those as well to figure out what a and phi are. And your book walks you through that a little bit. So anyways, I've given you enough of a background on what's going on with this. Now we can go ahead and start solving some of the problems, and we'll come back to this a little bit later. Let's start off with example 14.1 from your textbook. And example 14.1 says car springs. When a family of four with a total mass of 200 kilograms step into their 1,200 kilogram car, the car's springs compress 3.0 centimeters. See chapter opening photo. A, what is the spring constant of the car's springs, assuming they act as a single spring? And B, how far will the car lower if loaded with 300 kilograms rather than 200 kilograms? So that's the two questions. And this is a very typical scenario when you're using Hooke's law. They'll often give you a little bit of data about a force or something that can allow you to determine the force and what the actual compression or the spreading of the spring would be, the stretching of it, that is. And using that, you can determine K. And then they'll say, okay, well, with this force or with this stretch, what is this force or what is this stretch? And that's the normal scenario. So that's what we're doing here. So let's go ahead and show you what we have. And in this case, remember, F is equal to negative KX is all about that negative, is all about the actual direction. So we can drop that at will if needed. And that's what I'm going to do here. I'm going to say F is equal to kx. And in reality, it's really referring to the external force when we're talking about F equals positive kx. But again, it's you don't have to spend a whole lot of time thinking about that. You just need to make sure you know what you're doing when you're doing it. But normally, you can just drop the negative when you're trying to find out what k is. So what we found out is that we had a 1,200 kilogram car. Obviously, the car is already set at whatever spring height it has for the 1,200 kilogram mass. Once the people get in, it's going to stretch or it's going to compress the springs a little bit more. And evidently, for these 200 kilograms of people, it's going to be 3 centimeters. So what we're going to do now is we're going to plug that in. Now, the force is not 200 kilograms. Remember, weight is equal to mass times gravitational acceleration. So we're going to make use of the fact that solution, as I normally write, is F is equal to negative kx. We also have the F external is equal to kx. And we also have specifically that weight is equal to m times g. And that's what we're going to use here. So I'm going to say 200 kilograms times 9.80 meters per second is equal to K times, now we do want the units to be in, the fundamental base units for the SI system. So that's the kilogram for mass, even though it has a prefix. It's the meter for distance, and it's the second for time. So this is actually 3.0 times 10 to the negative 2 meters. And we can solve for K by saying K is, if we take the 19 or the 200 kilograms and multiply it by 9.8, we should get roughly 196, but we'll see. 200 times 9.8 gives me 1,960. Good thing I listened to myself on that one. So that's going to be 1,960 newtons, because that's what you get when you multiply 200 kilograms times 9.8, and then we're going to divide that by 3.0 times 10 to the negative 2 meters. So that's going to give us K is equal to, divided by 3 times 10 to the negative 2, and that gives me 6.53. Notice I carried one extra fig there, but that's 6.53 times 10 to the fourth, and the units turn out to be newtons per meter. And I'm sorry that 10 looks so bad, but I'll try to write it a little better. So that is our spring constant, and that is the answer to part A. And notice I did carry one extra sig fig, so if I need to use this figure somewhere else, I'm not rounding it and then using it and then rounding again and using it, so on and so forth. Now, that is our K, and in part B, they said, what would the delta X be in the event that the mass were 300 kilograms instead of 200 kilograms? So that's what we're going to do now. And notice how I'm using delta X and X interchangeably. That's very normal with F equals KX, Hooke's law type equations. In this case, we're going to say F is equal to KX, but this time we actually have the K. So what we don't have is the force yet, but we know how to calculate it. It's 300 kilograms times 9.80 meters per second, and that's equal to the K, which is 6.53 times 10 to the fourth newtons per meter, and that is multiplied by X, and that tells us, of course, that X is equal to 300 times 9.8 gives me 2,940, so that's going to be 2,940 newtons for the force, and now I'm going to divide that by 6.53 times 10 to the fourth newtons per meter, and you can see that when you divide a newton by a newton per meter, you get a meter. So I'm going to take this 2940 and divide it by 6.53 times 10 to the fourth, and that's going to give me 0.045 meters, which is 4.50 centimeters. Notice that's also completely consistent with what we expect when we realize the force is directly proportional to the X, or the X is directly proportional to the force. Our force went up by a factor of basically 3/2. Therefore, we expect the X to go up by a factor of 3/2. So if we actually took the original measurement, which is 3 centimeters, and we multiplied that by 3/2, we get 4.5 centimeters. So that's another way of doing it. I'm sorry I wrote that box in blue instead of red, but that's the second part of the result. Of course, I'd normally ask if anybody had any questions, but there's nobody here. So we'll move on. Now we're going on to conceptual example 14.2, and it says, which of the following forces would cause an object to move in simple harmonic motion? What you have to understand about simple harmonic motion is this force for the simple harmonic motion must be a restorative force, meaning if I stretch something in the positive x direction, then the force should try to pull it back to where it was. Therefore, the force should be in the negative x direction. If I instead push something in the negative x direction, the force should push in the positive x direction. So I need the x to be able to show a positive quantity or a negative quantity, and then not only that, I need the force to have exactly the opposite sign. That's sort of the key to having simple harmonic motion, and therefore we can look at these equations and see what's wrong with them. So they're actually asking specifically which ones of these could be used for simple harmonic motion. If you look at A, it's got that negative, so that's pretty helpful. But the problem is if you put in x equals, 3 centimeters, then you get 3 centimeters squared times zero point 0.5, and you get a force in the negative x direction. Well, that's good because I said the x was 3 centimeters, so I was pushing it in the positive direction, and the force came out in the negative direction. So that's good. But what if I put in negative 3 centimeters? If I put in negative 3 centimeters, again, in the proper units, because it's squared, I'm still going to get 3 centimeters squared because the negative times the negative is still a positive, and I still get a force pointing in the negative direction. So that one cannot work. So it would say no. Okay. If we look at part B or selection B, in this case, if we let y equal 3 centimeters, we'd see f would be negative 6.9. So that's good. If we said y equals negative 3 centimeters, then we see f would be positive 6.9. So that's good. So this one is definitely a candidate for simple harmonic motion. Notice how I wrote the SHM this time instead of SHO. Now, if we look at F, part C, F is equal to 8.6 times X. In this case, if we put in X equals 3 centimeters, again, 0.03 or whatever, we would multiply 0.03 times 8.6. And we stretch it in the positive direction, the force is still going to be in the positive direction, so it's now going to push it even further out. So that's not very helpful. If I tried the negative 3 centimeters, it's going to now push it even more in the negative direction. So this is sort of exacerbating the problem as opposed to bringing it back. So for this case, it's no as well. So that one cannot be a simple harmonic motion equation. Now, if we consider F equals negative 4 times theta, then you could imagine the theta could be, for instance, pi radians. If theta is pi radians, then F is going to be negative 4 pi. Uh, Basically for the force. So that's actually tending to pull it back to phi equals 0 or to theta equals 0. If we tried negative pi for the actual angle theta, then we'd get negative pi times negative 4, which would be positive 4 pi. And then, of course, some kind of constant. And the units of the 4 could be something. But the main thing is, in that case, we'd get a positive force. So this one is actually restorative like we need it. So B and D are the correct answers. These fit the simple harmonic motion requirement that we need. So that's how you do is conceptual example 14.2. All right. So we've now shown you basically how to work out the differential equation, and I've even hinted to you at what you would do in the case of simple harmonic motion with initial conditions. So let me now show you exactly what I meant when I said earlier, when I explained it in words, what was going on. So I'm going to separate this from the rest of the problem by drawing a straight line using our software. And now I'm going to go ahead and say, okay, let's consider a case, uh, initial conditions. Whoa, I forgot and left it on the function drawing the neat stuff. So initial conditions. Now we do call these initial conditions, but in reality, you could actually do them at t equal 2.5 seconds or t equals 0.03 seconds or whatever, and it wouldn't be initial then, but it'd still be an equation that you could use to satisfy, to basically make a system of equations so that you could determine the constants. But in this case, we're going to say at t equals 0 seconds, uh, x of t equals 0 seconds is equal to, just to get rid of that other problem, I'm going to say it's a sub 0. Now, that could be a number, for instance, that should be a number, and we're going to pretend like it's a number, but that's what we're going to call the position when t is equal to 0. And at t equals 0 seconds, v of t equals 0 seconds is equal to 0. So those are our initial conditions. So we had x is equal to a cosine omega t plus phi was our function, and we had v is equal to negative a omega sine omega t plus phi. Those are the two equations we already worked out. Remember, x, the velocity is x double dot, and we already worked that out. And just plain x is that. And we could do or excuse me, that's x single dot, not x double dot. There you go. So that's x single dot. And when, of course, we could take the second derivative, and that gives us the acceleration, but we don't have anything that we know about the acceleration right now, so it wouldn't be very useful. So now we're going to apply the initial conditions just to see what happens. So what we're saying is a0 is equal to a times cosine of phi, because when you apply omega t plus phi, when you apply t equals 0 to that, the omega t term just disappears. So I'm going to call this equation 1. Now I'm going to apply the initial condition about the velocity to the velocity equation, and in this case I'm going to get 0 is equal to negative a omega times sine of phi, like that, and that's going to be, for instance, equation 2. So, in some sense, we could actually figure out what this is. And what you could do, for instance, right now, we could look and say, if I just wanted to satisfy equation 1, then I could clearly just say phi is equal to 0, and then a is equal to a0. But we don't, that's going beyond what we know. We're sort of trying to double dip on the first equation so it doesn't work. But what we could do is we could, for instance, divide one equation by the other, all sorts of good stuff like that. But another way of looking at it is take equation 2, and we see that if we plugged if we let a equal 0, that would not be a useful solution at all. So this equation 2 is a much more useful equation. I can actually use that, and what we see is we need sine of phi to be equal to 0. And if you remember the graph of sine, it starts at 0, reaches 1 at 90 degrees, or pi over 4, or pi over 2, excuse me, and then reaches 0 again at pi, and then reaches negative 1 at 3 pi over 2, and then reaches 0 again at 2 pi. So we could say phi is equal to 0, but we could also say phi is equal to pi, or we could say phi is equal to negative pi, all those kinds of things. So this one implies phi equals 0 r plus or minus pi. Or you could go plus or minus 2 pi, so on and so forth. And we normally try to choose the smallest one that fits the criteria. So we'll think about that right now, and we might try plus or minus pi. So we'll say x of t is going to be a cosine omega t plus or minus pi, like that. That would work. Okay. But I'm putting the plus or minus in there because I'm not sure which one is the right one. Now, if I did that, that might actually work, but now I got to go back and figure out how does that work with number 1. So if I plug in number 1, then that would say a0 is equal to a cosine of plus or minus pi, and we see that that can't work because the cosine, let me draw these graphs real quick just so you'll recall what they are. So sine looks like this, and I'll say sine of theta looks like that. And you see that cosine, of course, looks like this. Okay. And if you look at plus or minus pi, what you realize is pi, cosine of pi is -1, and cosine of negative pi is also -1. So that doesn't really work for us. So we can't really use the plus or minus pi, but we could use possibly the zero. So we'd say x of t is equal to a cosine just plain omega t like that, and then use equation one, we'd say a0 is equal to a cosine of 0. And of course, the cosine of 0 is 1, so that tells us that a is equal to a0. So now we can say, therefore, x of t is equal to a0 cosine omega t. In other words, the phi is actually 0 for this case. And if we did that, then we could also see, because the initial condition required phi to be 0 or plus or minus pi or plus or minus 2 pi, the plus or minus pi and the plus or minus 2 pi would not work at all. Well, actually, let me see, plus or minus 2 pi. The plus or minus 2 pi, that could have worked. Yeah, I could have used plus or minus 2 pi, and that would have worked as well. But this would be the a solution. Again, you could also say cosine omega t plus or minus plus pi 2 pi, and you could also say a0 cosine omega t minus 2 pi. But why would you add a whole cycle? A whole 2 pi cycle there. The other thing to remember is when you're working with these, the arguments inside the trig functions have to be computed in radians. So that means your calculator is going to need to be in radian mode. So make sure you keep an eye on that. So that's one instance of how you could apply initial conditions. Your book does another one. It says, consider another interesting case. At t equals 0, the mass m is at x equals 0 and is struck, giving it an initial velocity towards increasing values of x. Given x equals 0 at t equals 0, we can write x equals a cosine omega t plus phi equals a cosine phi equals 0, which can happen only if phi is equal to plus or minus pi over 2. Whether phi equals plus pi over 2 or negative pi over 2 depends on v equals dx dt, which is negative omega a sine omega t plus phi, which equals negative omega a times the sine of phi at t equals 0, which we are given as a positive. Since the velocity is a positive, we have to choose phi is equal to negative pi over 2. So that's another case that we could do for an initial condition. And let me write that out here. So initial condition. So in this case, we're going to say at t equals 0 seconds, x of t equals 0 seconds is equal to 0, and v of t equals 0 seconds is equal to, let's say, positive v0. Okay, so if we remember that x is supposed to be a cosine omega t plus phi, like that, and the omega, again, that's something we know, it's the square root of k over m. For the initial condition, that tells us that 0 is equal to a cosine of phi, and then x double dot, or x dot, which equals v, is equal to negative a omega sine omega t plus phi. And according to the initial condition, that gives us a positive v0 is equal to negative a omega sine of phi. So there's our two equations. This would be 1 and this would be 2. This first equation could actually work, but this implies phi is equal to, if we again look at cosine, we actually need the cosine to be 0, and we can see that occurs at plus or minus pi over 2. Of course, we could also say it's going to occur at plus or minus 3 pi over 2, but why would we want to do that if we could do it with pi over 2? Now, the big thing is, which one of those is it? Well, we see now that the negative a omega times the sine of phi has got to equal a positive quantity. And if we look at sine for pi over 2, we see that sine for pi over 2 is only positive at positive sine, or at positive pi over 2, because the sine actually goes like that. That's what we call an odd function. So this is negative pi over 2, and this is pi over 2. So we actually need this negative. We need the sign of phi to be negative so it'll cancel out that negative. So I can take these two, the condition that we found above and the condition that we're finding right here, and say phi must be equal to negative pi over 2. Now, with that in mind, we can go ahead and say, all right, x of t is equal to a cosine omega t minus pi over 2, like that. And if we wanted to figure out what the actual amplitude is, then we need to go ahead and let a omega equal v0. So v of t is equal to negative a omega sine omega t minus pi over 2, like that. And in this case, this combines to give us the fact that V0 has got to equal A times omega, and therefore A must be V0 over omega. And finally, we can say x of t, this is the answer, I'm writing it in red, x of t is equal to V0 over omega cosine omega t minus pi over 2. I'm trying to erase some more stuff. Oh, there you go. Cosine omega t minus pi over 2, and that's the function. And it's obviously not writing very well at that low of an angle, so I'll write it over here. X of t is equal to V0 over omega times cosine omega t minus pi over 2. And that's the solution that we get specifically for this second set of initial conditions. Hopefully that helps you a little bit. And actually, you could do it for the more general case, which they show you in another diagram. I think it's figure 14.6. And that's when it's not zero at t, the x is not zero at t equals 0, and the v is not 0 at t equals 0. There's a general way you could solve these just by using symbols. And maybe I'll show you that. Maybe not. I'm not sure. You can definitely find it in some of my other videos, but I don't always do that. It's easy enough for you to do if you want to figure it out. I'm going to go ahead and erase this part at the bottom because as I was writing it, one symbol would disappear as I wrote another symbol. So if you look at it, you might get the idea that the wrong answer is the right one, and it's not. So, all right, now we're done with that. We're going to move on to now. We just finished example 14.2 before this, so now we're going to do example 14.3 now that we know a little bit more about the oscillations of the springs. And it says, example 14.3, determine the period and frequency of the car in example 14.1 after hitting a bump. It actually says 14.1a, so we're talking about the mass of the people is going to be an additional 200 kilograms. But the main thing is because we learned that omega is equal to square root of k over m, we need to know what the m is. So the m is going to be the 1,200 kilograms for the car plus the 200 kilograms for the people in it. So it says car springs again. Determine the period and frequency of the car in example 14-1a after hitting a bump. Assume the shock absorbers are poor, so the car really oscillates up and down. The movie Uncle Buck is coming to mind, so I would highly recommend you guys watch that. All right, so what we've learned from this is solution. We know that omega is equal to the square root of k over m, and what we're asked for is f is equal to question mark. And they're asking for the frequency, not the angular frequency. So I also need to remind everybody that omega is 2 pi f, so that means f is going to be omega over 2 pi. So if we go ahead and calculate what k is and what what m is, we can then calculate what omega is. We know k, for instance, we got, if I turn back, the k turned out to be 6.53 times 10 to the fourth. So I'm going to go ahead and write k is equal to 6.53 times 10 to the fourth newtons per meter. And I'm going to go ahead and say M is equal to 1,200 kilograms for the car plus 200 kilograms for the two people or the four people. So that's going to give us 1,400 kilograms. Therefore, omega is equal to 6.53 times 10 to the fourth newtons per meter divided by, and notice here we're actually using the mass. We're not using the weight. That's got to be what's in the omega is the mass, not the weight. So I got 1,400 kilograms. Now, a newton per meter is a kilogram per second squared. So then when I divide it by a kilogram, that just gives us a reciprocal second squared. And when I take the square root of that, that's going to give us a reciprocal second. And you know that we can just throw a radian in there. So that's what we're going to do. I'm going to take 6.53 times 10 to the 4, and I'm going to divide that by 1,400. And that's going to give me the square root of 46.64. We only had two sig figs really, so I'm going to underline both of those. And that is seconds to the negative 2 power. And now I'm going to take the square root of that by raising it to the 0.5 power. And that gives me 6.83 radians per second is the angular frequency. So that's omega, but we need F, and F is equal to omega over 2 pi. So that's going to be 6.83 radians per second divided by 2 pi. And remember, that's technically radians per cycle. So, in other words, by dividing by 2 pi, you're actually dividing by 2 pi radians per cycle. So it ended up giving you like cycles per second instead of just reciprocal seconds. So if I take this 6.83 and divide it by 2 times 3.14159, way more digits than we needed, but the main thing is I get 1.09. So 1.09 hertz is the frequency. And that's it. I think that's all they asked us for, right? Assume the shock absorbers. Oh, they wanted the period too. Sorry about that. So I also need the period, and the period is T equals 1 over F. So I can say the period is equal to 1 divided by 1.09 hertz. And if I raise this quantity to the negative 1 power, that'll give me 0.91 or 0.920. So 0.920 seconds is the period. And I really should have boxed this off in red, so I'm going to erase it real quick and do it again. So the frequency is 1.0 hertz and the period is 0.92 seconds roughly. Again, I would normally ask anybody if they had any questions. We would round this, of course, to 1.1. That's why it's not coming out to exactly 1 second for the period and 1 hertz for the frequency. So, anyways, let's go on to example 14.4. This one's kind of neat. This is where you can start to see even when something's not necessarily easily identifiable as a mass on a spring or something like that. If you see something oscillating like that, there's a good reason to think that it's going to have some kind of sinusoidal motion, and therefore it's going to be simple harmonic oscillation. And if it's simple harmonic oscillation, then we know we have certain things we can relate it to. For instance, we can say the angular frequency, which is, radians per second, is equal to 2 pi f, but that's also equal to a square root of k over m. And then, of course, f is 1 over the period, all sorts of good stuff. So in this case, they're saying spider web. A spider of mass 0.30 grams waits in its web of negligible mass. A slight movement causes the web to vibrate with a frequency of 15 hertz. A, estimate the value of the spring stiffness constant K for the web, and then B, at what frequency would you expect the web to vibrate if an insect of mass 0.10 grams is trapped in addition to the spider? So that's what we're going to do here, and we have solution. We know that, for instance, omega is equal to 2 pi f, and we know that omega is equal to the square root of k over m. So we could say uh, the square root of k over m is equal to 2 pi f, and that would mean that if I squared both sides, I would get k over m is equal to 4 pi squared f squared, so that we could say k is actually equal to 4 pi squared m times f squared. Now, this is sort of the nice way that theoretical physicists and people like us like to do it, work it all out algebraically and get a nice symbol so that we can see a nice formula so that we can see exactly how it depends on what. And in this case, we see the spring constant depends on the mass directly, so it's a linear relationship. If you doubled the mass, you would double the spring constant. However, it's proportional to the square of the frequency. So if you doubled the frequency, you'd actually increase the spring constant by a factor of 4. That's kind of helpful information. But the beautiful thing is we can actually now use this to just solve for the k. The spring constant for this is evidently going to be 4 pi squared times the m. Now in this case, it's just the mass of the spider in it, and that's 0.30. I need to use it in kilograms, so I'm going to say times 10 to the negative third kilograms, plus gram is 10 to the negative third kilograms. And then that is the only thing that's, well, that and the 4 is the only thing that's not squared. And then the frequency is 15 hertz, but that's going to be squared. So what we have here is 4 times 3.14159 squared times zero point 0.3 times 10 to the negative 3 times 15 squared. And that gives me 2.66, and that's 2.66, and it should come out to be newtons per meter is equal to the spring constant. And I'll box that off. And that was part A. Now part B, it says if mi equals 0.10 grams is added, what is the frequency? So in this case, we're going to go ahead and say we want to figure out what the frequency is. Specifically, omega is equal to the square root, or excuse me, omega is equal to 2 pi times the frequency f. But omega is also equal to the square root of k over m. So what we want to do here is we're going to go ahead and assume the k is the same, and now we're going to add an additional mass to it, so we have a different mass, and that tells us that the frequency is 1 over 2 pi times the square root of k over the m, which is 1 over 2 pi times the square root. Now I'm going to use the k that we just found, which is 2.66 newtons per meter, divided by, now instead of 0.3 grams, we're going to have 0.4 times 10 to the negative 3 kilograms. And I'll take 2.66 and I'll divide it by 0.4 times 10 to the negative 3, and that's going to give me 1 over 2 pi times the square root of 6,650, and in this case it's seconds to the negative 2 power. So that's going to give me f is equal to, I'm going to take the square root of that number, and the square root of 6,650 is 5 times the square root of 266, which is not that helpful, but it's also 81.5. So I'll just write that here just in case anybody has any problems when they're doing it. This is roughly 81.55 is what that is. Now I'm going to take that and divide it by 2 pi. So I divide it by 2 times 3.14159. I put all that in parentheses. You got to make sure you do the same thing. In this case, I'm going to get one, dang it, I changed that to blue already. I get 12 point, actually I might as well call it 13.0. That's 13.0 hertz is what the frequency should be when the additional insects on there. So instead of 15 hertz, it gets 13 hertz. So the spider would look and just see it going like this. But then once it actually had some potential food in it, the spider would see it go a little slower. He'd say, "Oh, I got reason to run out there and check my web." So that's how that works. Anybody have any questions on that? I don't know why I keep asking. I know nobody's here. It makes me feel a little bit crazy. Anyways, so one thing we might want to do just to make further sense of this is we've already figured out what sort of what the velocity is from our differential equations. So what I'm going to do is show something else. I'm going to draw a line to separate this out from what we were just doing. But we figured out already that when we're using simple harmonic motion, we have x of t. There I go, leaving it in the neat drawings method. X of t is equal to a cosine omega t plus phi. And we know that v is equal to x dot, and that's equal to negative a omega sine omega t plus phi. And now we could do the acceleration as well. And in this case, we're going to get, and we actually already did this previously, a is equal to x double dot. And in this case, it's going to be negative a omega squared cosine omega t plus phi. And that's our equations. Now, what we need to notice is remember that sine and cosine, they just oscillate back and forth between plus 1, 0, minus 1, 0, plus 1, 0, minus 1. They always do that. And in fact, what that number would be, or what the actual amplitude of the velocity or the x or the acceleration would be, is whatever number's in front of the sine or the cosine function. So because of that, we can see that V max is equal to a omega, at least its magnitude is. So that's something else that we now learn, and that's something that can come in handy. And we also see that a max, the maximum acceleration, that's going to occur again, and its magnitude is going to be a omega squared. So those are two more expressions we can get, and that helps us make some sense of how to figure out these motions. And not only that, we're going to see something kind of neat. Specifically, if you graphed, once you had a particular problem where you've worked out what a is and you've worked out what phi is, then you could graph x of t, and then you could graph v of t, and then you could graph a of t, all over top of each other with the t equals 0 lined up and the t equals 2 pi lined up, and you would see that the maximum x, which is amplitude a, doesn't line up with the maximum velocity. And you'd see that the maximum velocity doesn't line up with the maximum acceleration. And it's really important for you to understand exactly what those quantities are and why they're out of phase like that. I think you can make sense of it because I explained it to you when we set a mass in motion. Like if I pulled the mass out on the spring, I pulled it out to a positive x equals some amplitude, and then I let it go. Well, at that point, the x was a maximum, but the velocity was 0. So you expect when the amplitude is a maximum, that is when x max is when x is x max, you'd expect the velocity to be 0. And that's exactly the case because you've actually at that point had the maximum force acting on it, because force is proportional to x. And if x is the maximum, then the force would be the maximum. And for that, that would be where the object comes to a stop. So that tells you why the x and the v max are not lined up. But then what you also see is it'll start to speed up, speed up, speed up, speed up. And then when it gets to x equals 0, that's its maximum speed. So at whatever time you get to x equals 0, that's the time at which v is going to be v max. And then it's going to start slowing down, slowing down, slowing down, coming to a stop. Again, we're going to get x equals negative a in this case, and then the v max or the v is equal to 0 again. But like I said, when the x was a maximum, the force is a maximum, and since force is equal to mass times acceleration, you'd expect the acceleration to be a maximum when the force is a maximum. So it turns out when the x is at its maximum, you're going to have the a is at its maximum as well, but the velocity is certainly going to be at 0. So that's going to give you a different alignment, and that's something you need to think about. And your book does a good job of showing you that in graphs, but you should be able to draw those in graphs as well, just at the drop of a hat. That's a very straightforward conceptual question, as I could draw, for instance, the displacement x as a function of time, and then put directly below it v as a function of time, and directly below that acceleration as a function of time. And then you should be able to fill in what the velocity as a function of time is and what the acceleration as a function of time is. You should be able to do those two graphs from just looking at the first two graphs. Part of it's knowing about the fact that the derivative of the displacement is the velocity, and the derivative of the velocity is the acceleration. That helps you as well. Just to finish this off, I should say that x max is really just the a that we're talking about, and that's why we call it the amplitude. So I didn't feel right writing those other two equations without writing the x max equals a equation. Now we're going to go ahead and move on to our next example. Now that I've explained a little bit more about that, we're going to go on to example 14.5, a vibrating floor. A large motor in a factory causes a floor to vibrate at a frequency of 10 hertz. The amplitude of the floor's motion near the motor is about 3.0 millimeters. Estimate the maximum acceleration of the floor near the motor. Okay, so this is an actual real life engineering type problem. For instance, once you know the maximum acceleration, then you can sort of multiply that by a representative mass of the floor and the motor and that sort of stuff. And from that, you can get a maximum force. And in terms of like structural engineering, you can use that maximum force to estimate whether you need to support that engine with just 2x6s at 16-inch on center, or 2x8s at 16-inch on center, or 2x12s, or maybe even go down to 12 inches on center, all sorts of stuff like that. So it's a really good little engineering problem. So let's go ahead and write down solution. Oops, still in that nice drawing mode. Solution. In order to solve this problem, we need to know some information. For instance, we'll need to know omega is equal to 2 pi times f. That's how we get part of what we need. But in addition to omega being 2 pi f, we also need the maximum acceleration. And specifically, they're asking estimate the maximum acceleration. So I shouldn't need the v max, but a max is equal to a omega squared. So that's something we'll use as well. So with that in mind, let's go ahead and compute whatever omega is. So omega is equal to 2 pi times f. That's going to be 2 pi times 10 hertz. And of course, 2 pi is about 6.28, and we only have two sig figs, so 6.28 is enough. 3.14 being pi, and then 2 times pi would be 6.28. So 6.28 times 10 would be 62.8. So omega is 62.8 radians per second. And remember, it's sort of like that 2 pi is multiplying by radians per cycle, and the 10 hertz is cycles per second. So that fixes that. Now that we have that, and we have the amplitude, we can go ahead and say that A max is equal to A omega squared. So that's going to be 3.0 and times 10 to the negative third meters, because it was millimeters. And then I'm going to take that and multiply it by 62.8 radians per second, but that's got to be squared. So I'm going to take 62.8 squared and multiply that by 3 times 10 to the negative 3, and that's going to give me 11.8 meters per second per second. Again, we're just sloughing off the actual radians squared because a radian is not a true unit, it's a pure number. So that's what our A max is, and we've now solved that problem. Your book is calling that 12. Of course, that's exactly what we round it to, so that should work out pretty well. Now we'll move on to example 14.6. Starting with x equals a cosine omega t is what example 14.6 says. The displacement of an object is described by the following equation where x is in meters and t is in seconds. X is equal to 0.30 meters times cosine of 8.0t measured in rads or radians. Okay. Determine the oscillating objects A, amplitude, B, frequency, C, period, D, maximum speed, and E, maximum acceleration. So with this one, we need to know some stuff. Solution. For instance, we're going to want to remember that X is equal to A cosine omega t plus phi. That phi, by the way, is called a phase constant or a phase I think I heard him say even a phase factor or something like that. But I usually call it a phase constant. But it's basically just a shift of the cosine or sine function. And remember, for instance, if you shift the cosine by exactly the right amount, you'll get a sine. If you shift the sine by exactly the right amount, you'll get a cosine. So just remember that there really is no functional difference in sine or cosine other than the fact that they just shift by some phi. Okay, and you should work that out to figure out what it is. I always do it rather than memorize the identities. I just work it out in my head from looking at the graphs. But whatever you can do is fine. So in this case, we've got x equals a cosine omega t. So that allows us to just look at the equation. I can immediately identify the factor in front of the cosine as the amplitude. So the amplitude is going to have to be 0.30 meters. So I can go ahead and write that. But I want to figure out all the other stuff. So the other stuff I want to figure out is I want to recall that omega is equal to 2 pi f. And in fact, omega is what's being multiplied by the t. So we see the omega is actually 8.0. So I'm going to make use of that as well. I'm also going to remember that once we have the frequency, we can get the period by the period being 1 over the frequency or the frequency being 1 over the period. We're also going to make use of the fact that Vmax is equal to A omega and A max is equal to A omega squared. So that's what we got to go with. So A, for starters, we're going to calculate the amplitude, and we don't even have to calculate it. We just have to write it down at 0.30 meters. That's our amplitude, and that's just from matching the function that is supposed to be the simple harmonic motion equation, where we just match that with the form of it, which is A cosine omega t. Now we can go ahead and do part B, and we see that omega is equal to 8.0 radians per second. And notice if the 8.0 is really 80 radians per second and the t is in seconds, as it says, then 8.0 times t would work out to be radians. So that's a good check on making sure that we got all our units right. But now because I have that, I can now go ahead and figure out what the frequency is. The frequency f is, of course, omega over 2 pi. So that's going to be 8.0 radians per second divided by 2 pi, and that just converts it to hertz basically. So we're going to say 8 divided by parenthesis 2 times 3.14159 close parenthesis, and that gives me 1.27. Carrying one extra sig fig, of course, that's 1.27 hertz. And now all of a sudden my program's starting to change my drawings to make them pretty again. Really aggravated with this software package. All right, so we now have the frequency is what your book would call 1.2 hertz, and that's certainly fine. But again, I like to carry one extra digit in case I need that for a subsequent calculation, like the one we're getting ready to do now. Now for part C, we're asked for the frequency, or excuse me, we're asked for the period, and the period is 1 over the frequency. So I'm going to write 1 divided by 1.27. And now you see the handiness of having that extra digit is the fact that I can divide 1 by 1.27 instead of just 1.3. The 1.3 would make us like we're rounding twice, and that would be problematic. So I'm just going to raise the 1.27 to the negative 1 power, and that gives me 0.785. Again, notice I'm carrying an extra digit, so 785 seconds is the period. So now I can box that off. This is part A, this is part B, and this is part C, like that. So I now have C. Now that we have all that, we can go ahead and compute, for instance, we can calculate the Vmax, and we know Vmax is equal to A omega, and A we found was 0.30 meters, and omega is equal to 8.0 radians per second. So clearly this is going to be 2.4, and that is meters per second, and that's our Vmax. So now I've worked out the Vmax as well. To do the next part, we want the Amax, and that's straightforward enough. Amax is just A omega squared, which you might also notice is Vmax times omega, and that might make it a little easier for us. So I'm going to do that. 2.40 meters per second times another factor of omega, and the factor of omega was 0.30, if I remember correctly. No, that was the amplitude. It's 8.0. So 2.40 times 8.0 radians per second. 8 times 2 is 16. 8 times zero point 0.4 is 3.2. So 19.2. And that's meters per second, and that's our A max. So that's some of the types of problems you have to be able to solve from this chapter. And these are really the bread and butter type problems. These are the straightforward ones that often are the bare necessities. So definitely make sure y'all can at least do this sort of stuff. And we'll move on to example 14.7 now. So that was, yeah. So example 14.7. So example 14.7 says loudspeaker. The cone of a loudspeaker, figure 14.9, oscillates in simple harmonic motion, SHM, at a frequency of 262 hertz, which we know of as middle C. The amplitude of the central part of the cone is A equals 1.5 times 10 to the negative fourth at t equals 0, and at t equals 0, x is equal to A. Write an equation. Write what equation describes the motion of the center of the cone. B, what are the velocity and accelerations as a function of time? And C, what is the position of the cone at t equal 1.00 milliseconds? So what we have is simple harmonic motion. That's what that SHM means. And we have the frequency is equal to 262 hertz. And notice they said hertz, so that's the F frequency, not the omega. We are told that the amplitude is equal to 1.5 times 10 to the negative fourth meters. And we're told at t equals 0, x is equal to a. So we already figured out a little bit about that previously when we did our initial conditions. So A, they said what equation describes the motion of the center of the cone? So x of t is equal to question mark is what we're wanting there. And then B, what are the velocity and acceleration as a function of time? So we want V of t equals question mark, and we want A of t equals question mark. And then finally, part C, they want to know X of 1.00 milliseconds is equal to question mark. Okay, so that's what we're trying to figure out here. Solution, what we know is x of t is equal to a cosine omega t plus phi. And of course, we're told that uh, x of t equals 0 is equal to a. And we're told that a, of course, is equal to 1.5 times 10 to the negative fourth meters. So that's something that can come in handy. And they didn't really tell us what the velocity would be at t equals 0. But obviously it'd be something, but we might be able to figure that out. We actually already know what it is. For instance, we learned from initial conditions that x of t is going to equal a cosine omega t, phi is equal to 0, and then v of t is going to be negative a omega sine of omega t, like that. And we can actually figure out that a should be v0 over omega. And I'll just double check that where we did that initial condition analysis. At t equals 0, x of t is equal to 0. That what we said here. At t equals 0, no, x is equal to a is what we're supposed to get. So at t equals 0, x is equal to a. Yeah, that's right. And at t equals 0, v is equal to 0. And the way we were able to figure out that was that, well, that was about it. Oh, that's right. I was remembering the a was v0 over omega, but that was when at t equals 0, x is equal to 0. T equals 0, x is not equal to 0 here, so we can't use that. So I'm going to go ahead and erase that one. All right. So we learned from the initial conditions that that would be the case for this, and we weren't really told anything about the initial velocity, but we can certainly figure out what it would be. We know, for instance, the velocity at t equals 0, since sine of 0 is 0, is going to be 0. So anyways, with this in mind, let's go ahead and start with trying to figure out what x of t is, and specifically the x of t should be given by a cosine omega t, and I got to figure out that omega, oops, omega is equal to 2 pi times the frequency. We did learn that already. We specifically know the frequency, so it's 2 pi times 262 hertz. And 262 times 2 times 3.14159. And they really only gave us two sig figs on everything, so I'm going to call this 1650. So that's 1650 radians per second is the actual angular frequency omega. So now I can say that x of t is equal to 1.5 times 10 to the negative fourth meters times cosine of 1650 radians per second times t. And the phi is automatically 0 because of the initial condition that we worked out earlier, and I just showed you, in fact. So this should be part A, for instance. And now I can go ahead and say that A is equal to all this. Notice that also tells us since the 1650 is in radians per second and the t is going to be in seconds, when you multiply those two, you actually do get radians, which is exactly what we'd expect. So that's working out right. Now we're going to figure out what we want for b. Now b, its velocity as a function of time is x dot, and we can see that that's going to be 1.5. It's going to be a negative of this because the cosine, derivative of cosine is going to be a negative sign. So it's negative 1.5 times 10 to the negative fourth meters times the, oops, I need the omega now because remember we're taking the derivative of cosine omega t, which gives us negative sine times omega. So I've got to multiply this by 1650 radians per second times sine of 1650 radians per second times t, like that. Now we can compute all this. 1.5 times 10 to the negative fourth times 1650 gives me 2.2475. So this is going to be equals negative 2 point, or excuse me, negative 0.24. It's 7.5. I'm just going to call that 8 because that's one extra digit. And notice now the units of the sort of amplitude of the velocity is meters per second. It's actually really just the initial velocity or the maximum velocity. And then all of that times the sine of 1650 radians per second times t, like that. And that's our velocity as a function of time. And that tells us our initial velocity of our max velocity is about 0.25 meters per second, which is what the book is showing as well. So that's part B there. Now for part C, they wanted, or excuse me, for part B, they want to know the acceleration. So the acceleration of time is equal to x double dot, which equals d by dt of the velocity. So that's d by dt of negative 0.248 meters per second times the sine of 1650 radians per second times t. And I'm going to make this into a curly bracket instead of a regular bracket since I like to have a different symbol for each one. So now when I get that, I'm going to have a of t is equal to, now in this case it's negative and then derivative of sine gives you cosine, but it's going to be negative 0.248 times 1650. So times 1650, that's going to give us negative 408 meters per second times cosine of 1650 radians per second times t, like that. And that is our acceleration as a function of time. So I'll box that off, and that also is part of answer B. Now for part C, they want us to tell them specifically what is x at 1.00 milliseconds. So C, x of 1.00 milliseconds is equal to x of 1.00 times 10 to the negative 4. I'm trying to remember if they gave us 3 sig figs or 1. They actually did give us 3 sig figs there. So 1.00 times 10 to the negative third seconds is what we're trying to figure out. I can plug that into the x of t. That's going to be 1.5 times 10 to the negative 4. That's the only sig figs we had there, so I'm not shortening or anything. Times the cosine of 1,650 radians per second times 1.00 times 10 to the negative third seconds. Now, this is the part where we've got to remember to have our calculator in radian mode, or you got to take the 1650 times 1 times 10 to the negative third and convert that from radians to degrees, and that works as well. So I'm going to do it that second way, just in case you don't know how to do that. It'd be a better experience for you to see. So 1.5 times 10 to the negative fourth meters times the cosine. Now I'm take 1,650 and we'll multiply that by 1 times 10 to the negative 3. That's going to give me 1.65 radians. Now what I'm going to do is say this is 1.65 radians, but that is 1.5 times 10 to the negative fourth meters times the cosine of 1.65. I'm going to take that and divide it by pi and multiply by 180. So I'm going to say times 180 and then divide it by 3.14159. So taking uh, the 1650 times 1.0 times 10 to the negative third, which is 1.65. I'm taking that 1.65 and multiplying it by 180 and then dividing it by pi, and that gives me 94.54 degrees. And by doing it that way, I don't have to change my calculator mode. And I'm going to say cosine shift answer, and that gives me 1.5 times 10 to the negative fourth meters times, now the cosine of 94.54 degrees gave me negative 0.0791. And if I multiply that by 1.5 times 10 to the negative 4, that's going to give me negative 1.19 times 10 to the negative fifth meters is equal to x of 1 millisecond. So I get negative 1.19, or about negative 1.2 times 10 to the negative fifth is what that value comes out to be, and that's exactly what your book has. So hopefully that is pretty straightforward. You all understood that. Again, I would normally ask if you have any questions, but you're not here. So now we're going to go on to example 14.8, and here it is. Example 14.8 says a spring stretches 0.150 meters when a 0.300 kilogram mass is gently suspended from it as in figure 14-3b. The spring is then set up horizontally with the 0.300 kilogram mass resting on a frictionless table as in figure 14.2. The mass is pulled so that the spring is stretched to 0.100 meters from the equilibrium point and released from rest. Determine A, the spring stiffness constant K, and the angular frequency omega. B, the amplitude of the horizontal oscillation A. C, the magnitude of the maximum velocity V max. D, the magnitude of the maximum acceleration A max of the mass. E, the period T and frequency F. F, the displacement x as a function of time, and g, the velocity at t equals 0.150 seconds. So now I've got to write down all that information. We gave what we were told was that delta x when it's hanging is going to be 0.150 meters, and the mass that was actually hanging was m is equal to 0.300 kilograms, and then it's set up horizontally, and it's on a frictionless table, and the mass is pulled so that the spring is stretched to 0.100 meters and released from rest. So we're going to say x at t equals 0 is equal to 0.100 meters, and v at t equals 0 is going to be 0 meters per second, because they told us specifically the mass is pulled so that the spring is stretched 0.100 meters from the equilibrium point and then released from rest. So that tells us, one, that the x position was 0.100 meter at t equals 0 seconds, and then it was released at rest at that same time. So that means the initial velocity is 0. And now we're going to try to figure out a, we want to know k equals question mark, and we want to know omega equals question mark. Then part B, we want to know the horizontal amplitude. And I'll just write H-O-R-I-Z, so we'll know that. C, we want to know the maximum velocity. D, we would like to know the maximum acceleration. E, we would like to know the period t and the frequency f. And then F, we'd like to know the displacement as a function of time, so we want to know x of t equals question mark. And then G, we'd like to know V of 0.150 seconds is equal to question mark. So solution, what we need to know here is x is equal to a cosine omega t plus phi. We also need to know that omega is equal to the square root of k over m. We also need to know omega is equal to 2 pi f. And we also need to know that the period is 1 over the frequency. Since we were told that at t equals 0, x is equal to a, then we can also figure out that x of t is actually going to be equal to k a cosine omega t. In other words, the initial condition allows us to conclude that phi equals 0. Okay, so that will help us a little bit. I think that's pretty much. Oh yeah, we also need to know that V max is equal to A omega, and A max is equal to A omega squared, which is also V max times omega. Any of that will work. So we proceed as follows. First off, we're going to figure out K and omega. So when we hung the mass, we found that mg is equal to kx. So with that in mind, we're going to say 0.300 kilograms times 9.80 meters per second is equal to k times the stretch, which is 0.150 meters. And that gives us that k is going to be, I'm not going to write all the steps. I'm just going to do the math and tell you what the results are as I do them. 0.3 times 9.8 gives me 2.94. I'm going to divide 2.94 by 0.150, and that's going to give me 19.6. So K is 19.60 newtons per meter, and I'm carrying one extra digit, which happened to be 0 here. And now that I have that, I can also figure out what omega is. Omega is the square root of k over m. They did tell us they're going to use the exact same mass, so that's going to be the square root of 19.60 newtons per meter. Sorry about that. And then that's divided by the mass, which is 0.300 kilograms. Sorry about messing up that newton up there, but that'll give us radians per second. So I'm going to take 19.6 and divide it by 0.3. That gives me 65.33. I'm going to take the square root of that. Square root of 65.33 is 14 root 3 over 3, which is not what I want, but that does give me 8.08. Again, carrying one extra digit, that's going to be a 3 on the end, and that is radians per second is equal to omega. So now we've finished part A by getting the K and the omega. Now for part B, we're asked to find A, and of course we know A is going to have to be just the amplitude that we were given, so there's really no work to be done there because we know once we stretch it out to 0.100 meters, with it being frictionless, it's never going to get any smaller, but it's definitely never going to get any bigger. So A is equal to 0.100 meters is equal to the amplitude. So I'll just box that off. That's part B. And now we can do part C. And part C is Vmax. Vmax is equal to A omega. That's going to be 0.100 meters times the omega, which is 8.083 radians per second. And that obviously is going to give us 0.8083 meters per second is our velocity. So Vmax is equal to 0.8083 meters per second. Circle that off as part C. And was there anything else in part C? No, they just wanted Amax there. So now I'm going to do part D. Part D is where they wanted to know what part D they want to know. Oh, Amax. So Amax is equal to A omega squared, which is of course Vmax times omega. I'm going to use that 0.8083 meters per second times omega, and omega is 8.083 radians per second. I guess I could have written that radian a little worse, but not much. So 0.8083 times 8.083 gives me 6.53. And carrying one extra digit gives me 6.533. And that's meters per second is equal to A max. And now we've done part D. So I'll box that off. And now we're up to part E. E wants us to find T and F. Omega is equal to 2 pi F. So F is equal to omega over 2 pi. And we know omega is 8.083 radians per second. And I'm going to divide that by 2 pi radians per cycle. And 8.083 divided by parentheses 2 times 3.14159 gives me 1.286. Again, carrying an extra digit. That's the frequency in hertz. Your book would call that 1.29, and that is what we got. And now the period T is 1 over the frequency, so I'm just going to raise that answer to the -1 power. And that's going to give me 0.777. Carrying one extra digit puts a 3 on the end of that, and that is seconds, and that's our period. So there's part E, and here's part E. So now we're done with that, and all we have left now is part F, which is x of t, and part G, which is a velocity at a particular time. So F, we want x of t has got to be equal to the amplitude, which we already found was 0.100, times cosine of omega, and omega we found was 8.083 radians per second, and then all that will be multiplied by time, and the phi is 0. So that is what our actual function should be. We'll circle that or box it off. And now we're going to figure out what g is, and g is the velocity of 0.150 seconds. And that is equal to, remember the velocity is going to be negative a times omega, so that's going to be negative 0.100 meters, there's the a, times omega, which is 8.083 radians per second, times, now it's going to be the sine of 8.083 radians per second times 0.150 seconds. And again, this is a case where you normally want to use the put your calculator in radian mode, but we don't necessarily have to do that as I showed you before. So this is going to be negative 0.8083. Notice I am just repeating what we did earlier. This is meters per second. And all that is multiplied by the sine of 8.083 times 0.150 is going to give us 1.212, and that is radians here. But I'm not going to use radians. I'm going to take the radians and multiply that by pi over 180, or excuse me, multiply that by 180 over pi. So times 180 and divided by 3.14159. That's going to give me negative 0.8083 meters per second times the sine of, now that I've converted that 1.212 to degrees, it's 69.47 degrees. So I'll take the sine of that. That gives me 0.9365 times negative 0.8083, and that gives me negative 0.7570 meters per second is V of 0.150. So that is the result, and that's exactly matching what the book had as well. So we can be a little bit more confident that we didn't make any careless errors, even though that is a very common thing to occur. And we've now finished example 14.8. All right. I'm going to go ahead, and example 14.9 talks about a spring started with a push, and that's more or less the example I was talking about working for you earlier, where I can use initial conditions. And in doing so, I'm going to actually just do it generically instead of doing example 14.9. And I'm trying to see what else is left in this chapter. The energy of the simple harmonic oscillator. There's really nice equations that you should be able to use there. So it's really pretty straightforward. Uh, but I'm probably just gonna I'll just leave it up to you to work on your homework problems, and that should give you a good sampling of these energy ones. But I'm only going to cover sections 14.1 through 14.4, and then next time we'll cover chapter 15, or I'll choose to finish more of chapter 14. But let me go ahead and show you a general case of initial conditions. General initial conditions. So at t equals 0, x of 0 is equal to x0, and v of 0 is equal to v0. So we know x of t is equal to a cosine omega t plus phi, and we know that x dot of t equals v of t is equal to negative a omega sine omega t plus phi, like that. So initial conditions allow us to reach the following conclusion. We could say x0 is equal to a times cosine phi. I'm going to call that equation 1. And then I could also use the initial velocity being v0, and that gives me v0 is equal to a omega times sine of phi, like that. And again, that's at t equals 0, so that's why we only have the phi there. And that's going to be equation 2. So in this case, what I'm going to do is take equation 1, divide equation 2 by 1. And when I do that, I'm going to get v0 equals a omega sine phi divided by x0 equals a cosine phi. And from that, we get v0 over x0 is equal to a over a just cancels out, but we get omega times the tangent of phi. So with that in mind, we can go ahead and say clearly phi would equal the inverse tangent of, now I'm going to make a fraction out of this, and obviously to solve for tangent phi, we would divide both sides by omega, so that'd be v0 over omega x0, like that. And that's actually what phi is. So now we know that phi is equal to the inverse tangent of v over omega 0 times x0. And this is more or less like we're doing in example 14.9. And then we still need to figure out what A is, but since we have what phi is, we could actually use that, and we could say, for instance, imagine a triangle that looks like this and has this tangent of phi equal to this quantity. Then what we might see is, notice omega times x0 has units of meters per second, so it looks like a velocity, and that's what we're shooting for here. So I'm going to draw a right triangle, and I'm going to call this angle right here phi. And according to tangent, actually I should draw it better phi than that. And according to what we learned about the tangent is opposite over adjacent. So this would be v0 over omega x0, and this would be the square root of omega squared x0 squared plus v0 squared, like that. So now we can figure out that cosine of phi would actually equal adjacent over hypotenuse. That would be omega x0 over the square root of omega squared x0 squared plus v0 squared. Similarly, we could say sine of phi is equal to opposite over hypotenuse. That would be v0 over the square root of omega squared x0 squared plus v0 squared, like that. That's what cosine phi, that's what sine phi are. So with that in mind, we can actually use that to determine A. So if we look at equation 1, we could say x0 is equal to A cosine phi. So this is going to be, oops, this is going to be omega times x0 over the square root of omega squared x0 squared plus v0 squared, like that. And that gives us that A Notice the x zeros actually cancel out, leaving a 1. And we could say A is going to be equal to specifically the square root of omega squared x zero squared plus v zero squared, all of that divided by basically just omega. So we could do it that way, and that's basically it. But that is a general result. The phi and the a that we just got there are general results for any initial conditions. You just have to know the initial x value is x0, the initial v value is v0. Plug all those in, and you'll get exactly the right answer. And that's more or less what they're doing in example 14.9. Apply these to example 14.9 and see if you can get the same results. So that's sufficient there. We still have about 10 minutes left, but let me give you a little rundown on the energy since we can make use of that. Now, what I want to remind you about the energy is for a harmonic oscillator, we know that U is equal to 1/2 kx squared. And of course, we also know kinetic energy is 1/2 mv squared. So if we take x is equal to a cosine omega t plus phi, and we take v is equal to negative a omega sine omega t plus phi, then we could say E is equal to U plus K gives us the following. The total energy E is equal to 1/2 K times A squared cosine squared omega t plus phi. So that's me having plugged in the x squared, and then plus the kinetic energy part is 1/2 times m. Now I'm going to square the velocity part, and that would give me a squared omega squared sine squared. Notice the negative became positive. Sine squared omega t plus phi, like that. So we can see that E is actually equal to 1/2 k a squared plus cosine squared, and I'm going to leave off the argument there because there's just too much to write, plus 1/2 m a squared omega squared sine squared, again leaving off the argument there. The key thing I want you to see is omega squared is equal to the square root, or excuse me, is equal to, excuse me, omega squared is equal to k over m. Therefore, we see E is equal to 1/2 k a squared cosine squared omega t plus phi, and then plus 1/2 m a squared. Now, in place of omega squared, I'm putting k over m. You can see that the m cancels out with the m there, but we still have the sine squared of whatever. And that gives us, of course, now you can see it's basically E is equal to 1/2 k a squared, which is common to both of them, times cosine squared plus sine squared, like that. And you see that E is equal to just plain 1/2 k a squared. So that's one thing. That's E is just basically 1/2 k times the total amplitude squared. But that makes perfect sense, right? Because the energy is kinetic energy plus potential energy. But when you actually have the spring extended all the way out, it's kinetic energy 0, and all the energy stored up in kinetic energy, which is 1/2 ka squared. So that's one result we have. E equals 1 half K A squared. But we could actually do that a different way, and instead of replacing the omega with K over M, we could actually realize that that K is the square root of K, or excuse me, K is related to omega from this. So for instance, we have omega is equal to the square root of K over M. That implies that omega squared is equal to K over M, and that implies K is equal to M omega squared. Now, if we plug that back into this other equation, let me write it again. I'm going to write it in purple this time so you'll see we're doing something slightly different. This is 1 half K A squared cosine squared blah blah plus 1 half M A squared omega squared times sine squared, blah, blah, like that. Now what I'm going to do is replace the k with m omega squared. That's going to become 1 half m omega squared a squared cosine squared, blah, 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 plus 1 half m omega squared a squared times sine squared, blah, blah, blah. And you see finally that that's just 1 half m omega squared times a squared. Wait a second, the a squared should have disappeared. Oh, a squared, gotcha. And then that's times cosine squared plus sine squared, which is just 1. So we finally get that it's equal to 1 half m omega squared a squared times 1. But here's the kicker. Omega squared a is just our omega a is just the velocity squared. So I could say V max is equal to a omega, in which case we're going to have equals 1 half m times a omega is V max. So that's going to be 1 half m omega a, or excuse me, times V max. Oh, that's a squared. That's what it is. Sorry about that. So with that in mind, I lost the a squared. That was the problem. Darn it, it's supposed to be purple. So with that in mind, a squared omega squared is actually V max. So now I can go ahead and write it the way I meant to. Sorry about the little delay there. I'm just going to replace a squared omega squared. I'm going to replace that with V max squared. So so we see that the energy is also equal to 1 half m v max squared. So that should also make sense, of course, when the spring is taking its mass and pulling it right through the equilibrium position. When it reaches the equilibrium position, the potential energy should be zero, and all the energy is just the kinetic energy, and the kinetic energy is 1 half mv squared. And at that point, it's v max, so it's 1 half mv max squared, and that's what it shows here. So we can say either way, E is equal to either 1 half K A squared if you happen to have A, or you could say it's 1 half M V max squared if you happen to have V max. But the big thing is all of these different representations of this with the cosine squares and the sine squares, all those are fair game. So you can set the left-hand side for the E, you can set that equal to 1 half Ka squared, or you can set that equal to 1 half M V max squared. And then the other side is going to be all the stuff, the 1 half Ka squared cosine omega t squared plus phi plus 1 half M A squared omega squared sine omega t squared plus phi, or sine squared omega t plus phi. And you can use that to figure out, for instance, what the position is at any point in time based on the energy, all that good stuff. So that's partly what we're trying to show you with the energy methods that you see in examples 1410 and 1411. So I'll just say see examples 1410 and 1411. Again, when we meet next time, I may or may not choose to finish that by covering the rest of chapter 14, or I might just jump into chapter 15. We're going to do a quick and dirty version of 15 no matter what. Basically, there's just, it's a little bit more complex than this, but not a whole lot more. It's just a different equation. We're going to have what's called the wave equation, which is a second order derivative of something with respect to x equals 1 over velocity squared times the derivative, second order derivative of something with respect to t, because obviously v times t gives you x. So that's why it's the second derivative of that something with respect to position, or x squared, is equal to 1 over v squared times the second derivative of that something with respect to time squared. So the equation is slightly different. The only major thing will be, instead of it being cosine omega t plus phi, we're going to say it's cosine kx minus omega t for waves that are going in the positive direction. But for waves going in the negative direction, it'll be a cosine kx plus omega t. And you can see that that's the case by setting kx minus omega t equal to a constant and kx plus omega t equal to a constant, and then solving for x. And what you'll see is when you solve for x, you're going to get some linear function that tells you, basically by setting the kx minus omega t equal to a constant, that's a particular part on a sine wave. Maybe it's a peak, or maybe it's a midline, or maybe it's a trough, but it's just a part of the sinusoidal wave. And when you solve for that setting equal to 0, and you solve for the x, that tells you how the position of that peak, say, is moving as a function of time. And what you'll see is when you solve kx minus omega t equals to a constant for x, you'll see that the x is some fixed value plus something times time. So it's actually getting higher and higher and higher. And then when you do kx plus omega t, you'll see that the x is equal to some constant minus something times time. So you see that it's actually getting smaller and smaller. So the x is going in the negative direction. So that's something you need to think about. But that's enough for right now. Again, no one here, so can't really say I'm going to wait for the last person to leave in case anybody has any questions. But either way, everybody's free to go, and have a good evening, have a good weekend. Well, not weekend yet, but anyways, I did send an announcement today about the practice test that covers the material through the final exam as well. So that should be working now. Let me know if you have any problems with it. The pictures aren't loading, so on and so forth. Have a good day, and take care. Bye bye.